So I guess we are kind of ready. Yeah. So Professor Newell is an expert in the field of decision making, specifically cognitive processes underlying choices and decisions, which should not surprise you given that he agreed to participate in our DEB seminar straight from Australia, which makes our seminar truly international. So thank you for coming. It's not trivial given your time zone now. Professor Newell also recently published a new book, Straight Choices, The Psychology of Decision Making, in addition to numerous articles in top academic journals. So as I said, it's about 45 to 50 minutes for the presentation and then time for questions. And Ben, now the floor is all yours.
Thank you. Thank you very much, Shiffin, for the kind introduction, and thank you for the invitation to come and speak at this seminar. So the title for my talk today is Hidden Steps in Explanations of Behavior. And I've taken I guess a kind of bigger picture focus in this talk. And I'm going to try and go through a few, kind of taking a step back from the way that we normally think about our decision-making tasks and try to, I guess, stop and think about what it is we're trying to explain when we're doing our psychology experiments. What is it about the nature of our explanations that we're trying to achieve? So I want to start with I can advance my slides. I want to start with this photograph. So this photograph shows three people on a street corner, and we're going to say it's a street corner in Amsterdam in the middle of the 2000s. And we can look at this picture and we can think about, well, what are the aspects of behavior here? What are the things that we could try to explain? And of course, there's a myriad of different things that we could try to explain. Why are they there? What are they doing? Et cetera, et cetera. But I'm going to start by leaning in and listening to what they're talking about. And initially, I can hear that they're talking in English. And so we immediately have a question. We immediately have some part of the behavior that we'd like to explain, which is, well, why are these people speaking English? And we could try and answer that question. We could try and explain why are they speaking English and why not Dutch or German or Flemish. And it turns out that these three people, one's Bulgarian, one's Swedish, one's Finnish, but their common language is English. And so they're having a conversation in English. And we can think about this, why they're choosing to speak in this language by going back kind of through antecedent events. So we could say, well, English is the common language because they were all taught English in school. Well, why were they taught English in school? Well, because English had become a language that had been popularized throughout Europe for a variety of historical reasons, et cetera, et cetera. And we could almost go back a kind of infinite regress. And what we're trying to establish then are kind of laws to explain how each situation causes the succeeding one, causes the next situation. And this example I've taken shamelessly from a paper by Herb Simon, who used it in his address to the APS back in 1991 and 1992, in a paper where he was sort of talking about what counts as an explanation of behavior. And one of the things that he was pointing out there is that these kind of antecedent events or the sort of infinite regress that we could think about if we go back and back to try and explain behavior is often taken as a given in our experiments. So we don't want to sort of invoke those kinds of cultural events, those cultural phenomena when we're explaining the behavior we observe in our experiments. We take those kinds of initial conditions as given. So we take the contents or the organization of people's memories as a given. We're not seeking to explain at that level of analysis. But those givens, those assumptions, those things that we're taking as kind of read can also be important parts of our explanation of behavior. So one of the challenges, I guess, when we're trying to explain psychological behavior is that the thing that we're trying to explain, our minds, the way we learn, the way we behave, is an incredibly adaptive, incredibly flexible organism, if you like, or capacity. We have this capacity to create flexible, variable explanations, representations of our situations. And those situations are going to be affected by the experience we bring into the current situation. The experience that we've had doing similar things, the experience we've had in experiments, the experiences we get from these kinds of different interactions. And one of the challenges of psychology more generally is to go beyond the kind of common sense understanding we could get for why people behave in a particular way, and provide some sort of deeper level of understanding. And that deeper level of understanding can come from thinking about, well, what are the invariances? What are the laws of an adaptive system? So science often progresses by establishing laws, by establishing invariances. What are the things that are constants that we can learn across a whole variety of situations? And those laws are then things that we can build on, and we can build our explanations, and we can develop as a discipline, as a science. But of course, if the system that you're trying to explain is an incredibly adaptive one, then finding out what those invariances, what those unchanging things are, what those laws are, is tricky. And that is part of the challenge of psychological explanation. In the paper that I cited from Simon, he talks about this sort of challenge of figuring out the invariances, giving the following example. So he says, if you look at a packet of jelly, of Jello, can you see my cursor if I put it on here? If you look at a packet of Jello like this, you can't tell what shape it's going to be just by looking at it. But if you look at the mold that you're going to put it in, and you pour it properly and you do the mixture right, then you can have a pretty good guess. You can have a pretty good prediction of what the shape of the Jello is going to look like when you turn it out. Right? And if people were perfectly adaptive, if we were perfectly adapted to the situation, then the only thing we would need to look at would be the properties of the environment, the shape of the mold, the goals of the actor, what it is that the person's trying to do in a given situation. And from that, you'd be able to deduce kind of the optimal and therefore the actual behavior that you would observe in a given situation. The Jello has one goal to be produced, the properties of the environment of the mold, you can predict exactly what it's going to look like. And in some sense, that would sort of obviate the need for us to have any kind of experiments, because there'd be nothing left to predict if we knew that people were perfectly adaptable to the situation that they had. And you can think of this in the extreme as a kind of the approach that classical economics has taken, not experimental economics, but classical economics. It says, well, if you know what the properties are, you know the preferences of the actor, you know what they're trying to achieve, then you can figure out what the optimal behavior is, what the rational choice might be in a given situation. But of course, we know that people are not perfectly adaptable to different situations, and we have a multiplicity of goals and a multiplicity of actions that we can take in any given situation. And therefore, part of the kind of main challenge for cognition, and therefore the main challenge for us to produce these explanations of behavior, understand why it is people do the things that they do and understand what they're trying to figure out, is that rather than just looking at the mold, we have to figure out, as a participant in an experiment, but also as an experimenter trying to figure out the behavior, what aspects of the environment are important? How do people interpret those aspects, and how do people make decisions based on those aspects or features of the environment? And this is being talked about as the correspondence problem in both philosophical and experimental literature. So solving the correspondence problem is the idea of figuring out what it is, what's the right way to represent the world and decide and act accordingly. So what I really want to get into in the rest of this talk is think about what we can learn from how people are trying to solve this correspondence problem from the kinds of simple experiments that we often run and the behaviors that we can observe in those experiments. So I think it's fair to say that one way that we try to solve the correspondence problem for our participants is simply to make the task as simple as possible. So we kind of take out all of those possible cultural influences or contents of memory or misunderstandings of the way that the task might work by making things very simple and hoping that the participants in our experiments represent them in the same way that we're hoping that they will, and therefore that we can infer their behavior according to the kinds of representations of the task that we have as experimenters. So to give an example of a very simple task, this would be one that would be very familiar to many of you on the call. If we think about a very straightforward clicking paradigm task or decision from experience, where we show people two options on the screen, we don't give them any information about what these options are. We give them a very simple goal to try and end up in the experiment with as many points as possible. And we say, click away, and they find out that by clicking on one option, the one that's colored in yellow here, they're going to lose 10 points. And this is a situation where they find out what the other option would have given them as well, even if they don't click on it. In this case, it's 0. And they can carry on clicking. The next time they find out, okay, this one's -10, the other one, if I'd have clicked that, it would have been -20. So this is a simple instantiation of a decision from experience where we might set the environment so that one option loses you 20 points 50% of the time and nothing the other 50% of the time. The other option is always going to lose you 10 points if you choose it. So that's a very simple, seemingly simple task. But when we try to explain behaviors in this task, there are a number of steps. And what I want to emphasize today is that the kind of hidden steps that go into the explanation of that behavior. And some of those steps, I think, are underplayed in our current explanations. And some of the things that we think are going on, some of the assumptions that we bring into our explanations are, I think, probably a little bit overplayed. So for the participant in the task, they're trying to figure out, well, what features here are relevant? Is it that just the payouts? Is it the fact that I'm having to make these choices multiple times? Is something going to change in the environment as I go through? And what we really want to try and explain is how people are generating and evaluating representations of those tasks. And often the way that we think about it in our models, as the researchers or the experimenters trying to give these explanations, is we often invoke kind of probabilistic concepts in our explanations. So we think of people as sampling from outcomes. We kind of assume that they're learning probability distributions, that they're maybe perceiving randomness, and that they're judging likelihood. A lot of what I'm going to talk about in this first part is in a recent paper that I published with Abba Solosi and Chris Donkin. And this is work that has been driven in large part by Abba throughout his PhD. He's now at Edinburgh doing a postdoc with Neil Bramley. And part of what we're saying there is that these probabilistic concepts have started to go beyond being kind of a useful assumption in a model to an actual imbued in our explanations of behavior in ways that are perhaps not appropriate or not necessary, perhaps going past where their usefulness should be. And part of the reason for that is that we have a kind of broad history or these probabilistic models are used very broadly, very widely across lots of different situations, from modeling the climate to modeling pandemics to modeling traffic flows. All these kinds of things have been very usefully understood and approached by using basic probabilistic models in our explanation. And the way that these probabilistic models typically get used, the sort of logic of the application, is that they're used as an attempt to understand a complex physical system. We think of the processes in the probability model as trying to explain something about the underlying process in that physical system. And then once we've got that explanation, we can try and replace kind of relevant parts of that with probability distributions to make predictions. So we're replacing the relevant parts of the kind of complex physical system with these probability distributions that we're able to make predictions. And if we think about that in a simple case of modeling a six-sided die, then the sort of steps that we would take, we can define a sample space. This sort of represents the physical outcomes ranging from 1 to 6. We can expect in our model that one of these sides is expected to face up after the roll. Things like the die breaking are irrelevant for the purposes of our model. We can then define a random variable, which represents the physical process of the die roll. And we assume that the die is fair, the weight of the material is distributed evenly, et cetera, et cetera. And then we can replace these expectations about the physical outcomes with expectations about the model. So in the long run, we would expect all of the sides to be rolled a similar number of times. Now, there's no psychological aspect in that explanation. That's just about the physical system of representing what happens when you throw a six-sided die. But it's very tempting, and I think we do this a lot, to then sort of invoke similar types of explanations when we see what people do in these simple decision experience type tasks. So when we then start to apply these probabilistic models to behavior, we can look at going back to the simple task that we had before. So here's our clicking paradigm, and we can think about a participant going through this experiment, and this is like the first 14 trials of the experiment that they've completed. And we see this sequence of outcomes. This is full feedback, so they see all of these outcomes as they go along. And one way to represent what's going on for the participant in this task is to think of this as a kind of static representation. So nothing is going to change. Each trial is independent of the one previously, which is often the way that we actually program these tasks, but of course is not something which our participants will necessarily figure out or assume from the get-go. So if you have a static representation of the task, then you can think about just the number of times. If you assume that this right option is always going to stay the same, then the uncertainty, the thing that you're trying to solve, the part of the problem that you're interested in, is when am I going to see a -20 or a 0 on the other option? That seems to be the central thing for the participant. And if you assume it's static, then you could just do a very simple count of the number of times that I've seen -20, the number of times that I've seen 0, and then calculate some kind of probability that on the next trial, I'm going to get a -20. And we could think about putting that probability into our expected value calculation or whatever other kind of prediction we're going to use, a model we're going to use. But of course, another way to think about the task is that it's dynamic, that there's some sort of dependencies across these trials. And this is, I'm not saying that this is a revolutionary new way to think about it. There's lots of people who've talked about these kinds of issues in several ways, but I'm going to try and use this as an example to illustrate this nature of the explanation representation that people generate. So a dynamic representation is one where I think there's some kind of dependency between the number of times I've seen a 0 and the number of times I've seen the -20. And if I start to care about that sort of dynamic aspect, then I might start to look at the number of trials between bad outcomes. That's what this color coding on the figure is supposed to indicate. And from that number of trials, between bad outcomes, I might then start to think about, well, how could I calculate a kind of hazard rate or a likelihood of the bad thing happening on the next round? And that would be a very different way of thinking about how this task operates. And I want to argue that there are kind of the hidden steps in figuring out which of these representations people might adopt is really what we should be trying to answer in our explanations, because that's the problem that the participants, or one of the ways that the participants might be representing it. And which of those representations to use, a static or a dynamic one, is going to depend on knowledge about the physical environment and about the relevant kind of mathematical models, similar to the die throw. And usually, a few candidate representations can be identified. So how is the experimental environment set up? What's the researcher's goal? It might be from the perspective of the participant that if I've been asked to make this decision 150, 200 times, then presumably something's going to change across trials. Otherwise, why would the experimenter make me do it 100 times? why not just ask me once if it's the same thing every time? And people need to go through these steps in order to solve the task, but how they do that is not usually part of the probabilistic model. It's not part of the way that we then tend to invoke these probabilistic concepts in our explanations of behavior. And so the problem of missing out these steps is that we end up sort of focusing on modal responses. So we say, well, which representation do most people use? And this leaves the variability of why some people use this representation and not any other unexplained. And the modal response is taken as the kind of invariant, and the variability then gets explained away as a kind of nuisance variable. People do this with some kind of error. Now, I realize that if you end up going down this road far enough, then you could end up with a psychology of each individual's response to each kind of task that you ever give them. And there's a discussion to be had about how general any explanation could be. But I think by just saying, well, most people do it this way, so we'll focus on that, you are missing out a fundamental part of how it was that people got to that representation in the first place. The alternative approach that we go through in the site review paper and in this paper in TICS from the year before, previous couple of years ago, is to think about the idea that really what we're trying to explain in our explanations of behavior is that people can generate any kind of representation of a task. And it's that flexibility in generating representation that is kind of the fundamental building blocks of cognition and understanding. And so the invariants are, how people create them, and that can be variance increasing, but also how people evaluate them, and that's variance decreasing, so reducing the sort of differences in representations that people might have across tasks. And this is different from probabilistic approaches because we're saying now that the how and why representations change and how they're created is the thing that we're trying to actually focus on rather than explain away. And that the representation that people currently use is only going to provide a very small window on this process and not the end goal. And that this kind of amplifies also the importance of background knowledge. So it's sort of bringing back some of the stuff that I was mentioning with the conversation with the cyclists at the start, that, yeah, we don't want that kind of infinite regress to, well, why were they speaking English? Because England had a large empire. But there's a point at which we do want to also think about, well, there probably are some cultural influences here as to how people are interpreting the environment they're in and how they're figuring out what's going on in the experiment. And to ignore them is to reduce, I think, the richness of our explanations. So a non-probabilistic explanation is saying that this representation building is going to be constrained by the kind of communicational norms, the information that people can get from the instructions that they get in the experiment, the way the situation is set up, because people tend to emphasize relevant information in communications. It might also be constrained by knowledge of very simple mathematical principles, so not understanding probability distributions or independence across trials or anything like that, but just simple kind of counting, keeping track, frequency. And it's also going to be constrained by the kind of feedback that people can get from their interaction with the task. And that feedback can be helpful if it's diagnostic in terms of the representations that people might be entertaining of what's going on in the first place. So if they can gain some understanding from their interaction with the task, then that's going to be this sort of variance decreasing force on the representation that they have. So this is probably all sounding a bit abstract at the moment. So I'll try and give you a sense of the experiments that we have in the paper that try to put a little bit more of a concrete focus on how we see this changing in representations and this kind of convergence on a given representation to be occurring. So the question that we're asking is how environmental feedback, so how my kind of interaction with the task helps in constructing and improving representations of the unknowns in a given environment. So we ran two kinds of experiments. One that I'm going to call temporally unstructured feedback, which we propose is going to lead to more unconstrained representations of the task, and one which has temporally structured feedback, which should lead to more constrained representations of the task. So what does that mean? Well, the task that we gave people is the one that I was illustrating from the start. So, but with a slight extra feature to it. So our participants went through a kind of standard decisions from experience type task, a repeated choice task, where they're choosing between these different options. One option always has, always has two outcomes, and the other option is always fixed. It's a sure thing. And then once they've completed some number of trials of that task, we then get them to do a sequence generation task. So this is trying to extract, if you like, or get them to actually tell us what their representation of the task looks like. So in the sequence generation task, we said, think about the options that you've seen on this, this one button that had the two outcomes, and try to produce a sequence which looks like the one that you've just experienced. And so they had to then generate sequences of outcomes that would map onto the sequences that they'd seen. So this is trying to get at that, what does their representation of the task look like? The manipulation of the unstructured and structured feedback is like this. So in the temporally unstructured feedback, we gave people problems where there was no there was no kind of fixed order in which these outcomes were appearing. So in a version like this, there's a 50% chance of getting the -20 or the 0 on any given trial. And we had different problems with different probabilities of the two outcomes or the risky outcome. And this is a plot showing the density of the outcomes of this rarer event, or equal event in this case, since the most recent bad outcome. So you can see that there's no kind of fixed repeating pattern here. There's just a distribution over where this event could happen across the trial. So there's not really much feedback that would allow you to constrain your representation of what's going on in the task. So the -20 could be appearing here, or it could be appearing after 3 zeros, and so on and so on. So it's not giving you any structure to learn. In contrast, in this temporally structured feedback version, there was some pattern in when these rare bad events were going to occur. So in this particular instantiation, you would see the -20 on every fourth trial or 0 otherwise, and in the other key, it would always be the -10. So we did various different versions of this temporally structured feedback by changing aspects of the environment that we thought would either help or hinder people's ability to basically build up the representation of what's going on in the task. So the one that I just showed you was this one, a unimodal distribution with a probability 0.25 of the rare event happening. So that's every fourth trial, you see the rare event occurring. We also looked at bimodal distributions, and we also looked at ones where there was it was completely discrete, so there was no other possibility of the rare event happening, or where there was some noise in the distribution as well. And again, you can think of these factors as helping people, if you like, to understand, to build that representation of what the task is actually looking like. So what do we see when we give people these two tasks? Well, when we look at first at the temporally unstructured feedback, what I'm plotting here is the risky choice proportions as a function of the trial since the most recent bad outcome in 3 different problem types here, with the probability of the risky, rare loss being 0.15, 0.25, or 0.5. The solid black line is the choice rate averaged, and the dotted line is the hazard rate that we've calculated as a kind of proxy for people's expectations of when the bad outcome is going to occur. And this is averaged across all of the sequence generation tasks that people did. So what you can see in the aggregate level is a kind of relationship, especially in the p equals 0.251, but in some other cases as well, where as the hazard rate sort of goes up on the average, the more they expect the bad thing to happen, the choice of the risky option goes down. We also see evidence for the kind of wavy recency effect that Ori and others have documented, where straight after the rare event happens, there's this uptick in the risky choice. But you can see the colored lines here, the individual choice rates, and the degree to which each individual is kind of entertaining that same representation of the task and following that same kind of pattern of an increase followed by a tapering followed by a decrease is wildly different across lots of different individuals. Now, whether you treat that as noise or whether you treat that as something interesting as to why it is people have generated these different representations of the task is I think the point that I'm trying to get at throughout the talk today is what does this mean about how people are trying to figure out to solve that correspondence problem. If we then turn to the temporally structured feedback, so now when there was a pattern, if you like, within the sequences and a way to help structure that representation, then we see for at least some of the problems, the unimodal ones in particular, we see a much tighter congruence between different individuals and their risky choice rates, and also this relationship between the hazard function and the choice rate. So now we see a very clear kind of negative correlation in all of the cells, some more stronger than others, whereby as this hazard rate goes up, the choice rate goes down, and people have kind of figured out the structure, especially when you take the noise out of the environment, you make the distributions discrete, you make it unimodal rather than bimodal. People obviously still have difficulty tracking the bimodality, especially when their events are quite rare. But in general, the idea here is that as you reduce the amount of variance that people can have to try and establish their representation, so you see a clearer pattern of behavior coming out. So more people are kind of converging on the representation of the task that you, as the experimenter, wanted them to, in a sense, wanted them to figure out. So I think this way of kind of looking at the data or structuring the experiments helps us to uncover some of these hidden steps. It highlights some of this sort of representational variability that you get in temporally unstructured environments. And it shows how that environmental feedback can help improve people's representations by constraining the hypotheses that they're testing to evaluate them. So that's reducing the amount of noise in their hypothesis evaluation, because you're guiding them to build up that representation. But that's only clear, it only happens when it's clear and relevant for the general representation that people are entertaining of the task. So you're only getting that guidance if there's a kind of match between the way that they're construing the task and the way that the feedback is operating. And that, I think, goes closer to the kinds of things that we want to explain when we're understanding how people are interacting with these kinds of tasks. I now want to move to let me just check, how am I doing for time? I don't actually have a clock up in front of me.
You're fine with time, you have about 15 minutes. 15
minutes left?
Yeah.
Yeah, okay, perfect. So now I want to talk about another set of experiments that we're currently writing up. This is work with Alice Mason and Abba. And this is sort of taking a step even further back from looking at the representations in the decisions from experience type tasks, but actually to focus directly on how people construct representations of distributions, or whether they can construct representations of probability distributions. So again, we often assume that people are representing things in some way that conforms to a probability distribution that they may be sampling from, and some models are very explicit in the way that they talk about that. But experiments that look at whether or not people can acquire distributional knowledge is pretty rare. It's not really focused on very much. There's an exception in this paper by Tran, Vull, and Pashler, which was kind of the inspiration for the work that we did. So I'll just talk you through how we looked at this distributional knowledge learning. So in our task, it was very simple. There's no choice element to it. It's simply a task where we're getting people to experience a distribution and then asking them to recreate it. And what we're interested in is whether they can recreate this distribution with the properties that they've been exposed to in the initial task. It's intentional in the sense that we tell them that you're going to have to recreate this distribution, but it's not. There's no choice task. There's nothing like that. So what they do is they look at the screen and they're told there's a dot that's going to come down the screen, and you're going to have to click on this dot and see what the outcome is. And it's going to be a number. And as they go through, they can click on it, the number is revealed, and then the number stays on the bottom of the screen.
But they are told in advance that the distribution are static?
They're not told anything about the static or dynamic nature of it. They're just told you're going to see some numbers, and then we're going to ask you to reproduce it.
Okay.
So they do this, and they then at the end of seeing all these numbers, we say, okay, here's a number line. Please generate the numbers that you've seen in the same kind of way that you've seen them. So we're not saying just show exactly the same thing, but we're trying to get them to think about what distribution have you seen, and you can move this counter up and down until you've generated sufficient numbers. The distribution that we actually show them is a noisy bimodal distribution. This is taken from the paper by Tran that I mentioned. So the lower mode has a lower mode and an upper mode. The lower mode is numbers between 10 and 26. The upper mode is numbers between 80 and 84. And they're presented 7 times, the other one's 4 times. And then they see all the other numbers between 1 and 99 1 time each. So there's 180 numbers in total. So it's a noisy bimodal distribution. And then what we did across 5 different experiments was to try to kind of, in the same spirit of using that temporal and temporally structured feedback, we tried to give them kind of additional scaffolding, additional instructions and environmental feedback that would help them to represent this distribution in the way that it had been presented to them, to try and get them to sort of understand what distributions look like and whether or not they can actually reproduce them. And we did this because in our initial experiments in the baseline, where we didn't really give them any additional information, as I'll show in a minute, people weren't very good at it. And so we then built up the amount of extra information that they got. We gave them a kind of frequency hint saying, some numbers are more likely to appear than others. We gave them this frequency plus telling them there are 2 groups of numbers. Then we did things where we gave them the numbers in the modes were different colors to the numbers in the noise. And we gave them a reward that was linked to remembering numbers in the modes rather than numbers in the colors. And then the last experiment 5, we gave even more kind of cues, if you like, to the structure of the environment, to give them a hint, to give them modes and noise in 3 different colors. So the low mode and the high mode was in a different color and so on. And the point here is that, if in our models we're thinking of people learning probability distributions or representing things as probability distributions, then it's important to try and understand how easy or difficult it is to actually get people to represent things in that way. And it turns out that in the baseline condition, where we just say, here are the numbers, please look at the numbers, and then try to reproduce a distribution that retains the properties of the ones that you've seen, people are horrible at it. So this, in the back here in the gray, is the actual distribution that they've seen. This yellow is the aggregate of the distribution that you get from each person's generated distribution. So you can see that they're producing a whole lot of numbers that they've never seen, or more times than they've ever seen them, and they're barely capturing the bimodality in the distribution at all. This is similar to the results that Tran et al. Found in their version of a similar kind of task, that people just were not able to do this very well. It wasn't until we gave people all of the hints, so kind of down here in experiment 5, that we saw people actually recover or be able to reproduce the distribution in the way that they'd experienced it. So there's still some evidence that people are producing numbers more than they've actually seen them, but now we do see a clear capturing of the bimodality in the distribution. Our other attempts to do that in experiments 2 and 3 and experiment 4 didn't really seem to be enough of a scaffold or enough of a hint to get people to understand what was going on or be able to reproduce it in the way that they'd experienced it. So, and there's multiple other ways to look at these data. This is a KS value comparison. So this is measuring the distance of the distribution, the average distribution that people produce from the underlying distribution that they'd experienced. And you can see that in experiment 5, the KS value, so lower here, 0 means that it matches the distribution that they've seen. And you can see in experiment 5, the KS value is lower. Across experiments 1, 2, 3, and 4, we didn't really shift it very much at all. You can also see this in cumulative probability. So these are cumulative density functions. And again, you can see here that so this is the underlying distribution, and this is the average of what people produce. The yellow is the average, the gray is the underlying, and these are individual lines. And you can see that, again, there's lots of different ways that people are representing this problem or trying to solve this task. And it's not until we give them sufficient scaffolding, sufficient kind of environmental feedback over here that they can constrain those distributions, constrain those representations to the point of actually figuring something out and looking as though they've learned the distribution or at least representing it in a way that's consistent with it. Having said that, even when you then go in and look at individuals across all of the experiments, so these are now individual plots of the distributions that people produce, there are different strategies, again, that people can take. There are different ways that people try and solve this problem. And even in the 5th experiment, this one on the lower left, you can see that some people are still kind of producing a uniform distribution and not really capturing the bimodal properties. So by drilling down into these representations, you do get a better sense of what people are doing, how they're trying to solve these tasks that are in front of them. Another way to get them to learn it, was another experiment that we did, is just to remove the noise from the environment completely. So then we gave them a discrete bimodal without any additional scaffolding or hints. You can see that people are actually able to capture what's going on quite well. So I think one of the things that we see here is that this means that this distributional information is not acquired implicitly or even intentionally, but environmental and instructional feedback is crucial for building the representations. And I think that suggests at least a bit of a mismatch between the role that we play in our psychological explanations for people assuming things are distributed in this way, or the way that we use them in the models, and the way in which this acquisition occurs or indeed doesn't really occur. Okay, in the interest of time, I'm going to skip this next one, but you can ask me about it at the end, because I'm going to jump to this, which is the last kind of point that I want to try and make. So in the last few minutes, I just want to try and make a link between this idea that we need to sensitively measure people's task representations and understand how it is that these representations are developed and that they figure out what's going on, actually brings me back at least to work that I did very early on, right back in my PhD, looking at claims about what people can learn implicitly and how people can behave and do things that are completely outside of their awareness. So how much of behavior is controlled outside of awareness, which might seem like a bit of a leap, but bear with me and I'll try and convince you of it. So what I've got here on the screen is a thing called a finite state grammar. And there was lots of work done in the 60s and 70s on how claims made that people could implicitly learn these kinds of representations. They were able to determine or distinguish between grammatical letter strings and non-grammatical letter strings, but have no awareness of the underlying rules or how they did it. And the claim was that people had acquired these kinds of representations of grammars implicitly. But then subsequent work actually sort of drilled down into the representations that people were using in these tasks and found that, in fact, people hadn't acquired these complete rules in any sense. They just got sort of fragmentary knowledge, and that fragmentary knowledge that a T couldn't follow an X or an X couldn't be preceded by a P or whatever it was enough to explain people's behavior. But it wasn't until there was that sort of digging into the representation and the link to what people understood about how they were doing the task that these kinds of claims about awareness were started to be questioned. Now, despite all that work going on, it's still surprising to me how much we see explanations out there, explanations of behavior that rely on claims about things going on outside of our awareness. And so we go back to our friends on the street. We never found out what they were talking about. And it turns out that one of them is saying to his friend, "I've got no idea why, but I really feel like a beer." And his friend says to him, "Well, that's because you just rode past that Heineken sign and you've been unconsciously influenced. You've now been sort of primed to want to have a beer." So remember, this is in Amsterdam in the mid-2000s. So this person's obviously been following the Dutch experimental psychology at the time. And these kinds of claims about things being primed outside of our awareness are still very prominent, and there's lots of books out there that have this general line that run through them. The John Barge one is a very clear claim along those kinds of lines, that before you know it one. And so I guess out of frustration more than anything else, David Shanks and I have recently been working on a kind of can't beat them, join them book. So we have got a book coming out next year, which is trying to actually go a bit more directly and look at the evidence for when is it that you actually see these kinds of effects occurring outside of our awareness. And if you assess the representations that people are actually using to support behavior in these tasks, then you find that these claims don't really hold water. And we're linking that to the kind of replication crisis and theory crisis and other crises that have been invoked across psychology recently. So that's a bit of a plug for that, and the idea that links again into this hidden steps idea. I'll jump through this because I know I'm running out of time. But the hidden steps is the idea that we can invoke these kinds of unconscious mental processes to explain what's going on, but those unconscious mental processes are kind of like dark matter in our explanation. So we infer that they must be there, but we have no real explanation of what they're doing or why they're in there. And what we argue in the book is that if you can understand behavior in terms of conscious knowledge, beliefs, and attitudes, and that gets you a very long way, and it pushes us more towards thinking about the fact that people are, and this is my final slide, are kind of acting as what we've described as intuitive scientists in a couple of the papers with Abba and Chris. So people are trying to solve the problem that's in front of them, and that the invariance in adaptive systems like ourselves is that creation, modification, and updating and flexibility of those representations. And it therefore focuses more on the creation and evaluation of those rather than assuming this sort of fixed representation. So that moves us away from these probabilistic assumptions that have often been invoked before in the kind of intuitive statistician metaphor. And I think it also reduces its role for unconscious mental process, because unconscious thinking is just a bit of a kind of category mistake if you take this view that people are actively trying to solve the correspondence problem in front of them and think about what they're trying to do. And it also has implications for subtle behavioral interventions like nudging But maybe I'll leave that for questions if you want me to go into that in any more detail. I haven't been watching the audience as I've been going through, so I don't know whether people are still there, but that's all from me. So I'll say thank you very much to these people. Joel's a current PhD student whose data I skipped over, but I can go back to. Those are the papers if you're interested, and thanks to the Australian Research Council for the funding, and thank you for your attention. Over to you.
Thank you. Excellent time management skills. I will have to learn from you. So
it's good because
now,
I didn't have a clock in front of me either, so I was guessing.
no, you're exactly on time. Very good.
Perfect.
Yeah. So now, guys, it's time for questions. Yeah. Actually, most of the people are still with us. So if you have a question, you can type it in the chat or raise your hand. Priya was the first, I think.
Yes, Professor Noel, many thanks for your talk. I have two questions. One is on the experiment itself, and one is on the last few points you mentioned. So the first one on the experiments, is there a role for memory? Because people can have different levels of memory that can affect the distribution they create, and many people remember only the most recent ones. The second one is, do people represent in pictorial form, so that when the sequence is, let's say, 1 0 1 0 0 1 and so on, in some form there is a pictorial representation, and that is easier to remember, so that can also create these differences.
Yeah, both good points. I mean, there's clearly, if you're talking about the distribution, well, both sorts of experiments, but certainly in the distribution kind of learning experiment, there's clearly going to be some role for memory for how you're encoding the events. I mean, the way that we tried to give people instructions was not, remember the exact sequence that you saw, or remember all of the numbers in the exact way that you saw them, but to try to generate as if you were carrying on clicking on this button and it was going to give you more similar outcomes. What would it look like? Or in the distribution one, it was try to create, a represent one. We didn't use representative, but try to create something that looks similar to what you've just experienced. So to some extent, yeah, people's memory is going to play a role. We didn't look at things like working memory capacity, but that might be an interesting variable to follow up.
Okay. And on the pictorial representation, do you have any comment?
Yeah, I mean,
there is this
yeah,
verbalizer, visualizer kind of dichotomy or something.
Yeah, I mean, again, we didn't kind of give people strategies for how they might do it, but I guess one might be that they could try and chunk it visually, or think about how the components fit together in that kind of way. Yeah, I think that could be something.
Okay, and the last comment, so it's more like a comment rather than a question. I think I'm more towards the camp of Barg and people like that. The research that I do, generally I have a tendency to believe in unconscious, people have unconscious processing. And so your paper with Shanks, I had actually cited it and it doesn't support my logic, so I have removed it and so on. So would like to read a lot more from this and learn from you. So maybe I will reach out at some point. Thank you so much for your talk.
Please do. Thank you.
Elliot, good to see you.
Hello, Eufeme. I don't see you, but I do see Ben. I don't know if you can see
I'm
me.
going to stop. Shall I stop sharing and then go to the...
You see the more beautiful guy out of the two of us, so it's fine.
Hi, Ben. Thanks for the very interesting talk, as always. I had a question about the first part. Maybe I should know the answer to this, but the question was, when you were giving the unstructured ones, did everybody get a different random sequence, or were they getting the same random sequences?
We had a number of different random sequences, so they weren't all uniquely generated, but they weren't all were not all the same. So it's
you might see where I'm
between.
going with the question was because obviously with the structured feedback, they all do the same thing, but they also all got the exact same sequence almost, right? Modulo the noise. So in the random one, question is, if everybody had the exact same random sequence, would you perhaps see less of that heterogeneity across people, and maybe more convergence on a single type of representation in that space?
I mean, it's an interesting question, right? Whether people will converge to randomness if they're seeking structure.
I mean, if it's the same, because it's not, I mean, there is, I mean, you call it random, but it's just a series of numbers, right? The generative process was random, but the actual outcomes is just what they see. And so yeah, no, it's just, I don't know, I'm wondering if you had done that and looked at that, but if you haven't, you can't know the answer, obviously.
Yeah, we did. We were sensitive to the idea that if people were all given the same random sequence, then it would be problematic. So that's why we sort of ended up with that kind of compromise. But yeah, it's an interesting thing to follow up on a bit more directly. I agree.
Okay, thank you.
Thanks.
Good to see you.
Yeah, likewise. Really good to see you.
Okay, good to see you as well.
Thanks. So yeah, great talk, Ben. Of course, a lot of my work is very much relevant, but I want to focus on something that you said in the very last slide, I think. So you made a distinction between intuitive scientists and intuitive statisticians. And it seems to me that intuitive scientists, you mean that people are trying to entertain whether their hypothesis regarding the model, regarding the environment representation that they have in mind is reasonable. And how do they do that without any statistical intuition? So wouldn't that, how do you entertain this hypothesis testing that seems to be going on in the intuitive scientists' idea?
I think with the distinction that we try to draw is that in the intuitive statistician metaphor, it's often assumed that there's a kind of static representation of what's going on. So you have a representation that's determined by some sort of statistical properties, and then you're trying to figure out whether that's the suitable one, right? Whereas the intuitive scientist idea is that you don't bring that kind of machinery already to the problem. You're a further step back in trying to figure out, well, what are the things that I should be looking at in this environment in the first place? Whereas the intuitive statistician is saying, well, there's a sequence, some things appear more frequently than others. I'm going to infer straight away what part of the sequence it is that's important, or what counts as a sequence. Is it 5 events? Is it 10 events? Is it? Whereas the intuitive scientist thing is trying to step back from that and say that there's more kind of fundamental questions that we're trying to ask and entertain and test and evaluate in our representations.
So it's kind of like a distinction between coming up with a model into the world and then trying to fit it, or rather finding a model that explains the world. Is that what you mean?
Yeah, that would be one way to construe it. Yeah.
Okay, thanks.
Thank you.
Duh.
Do I still have time? I see we have only 1 more minute. So let me just make a...
Always time for you, Ido.
Okay, I plan to make something, make a very smart point, but I don't have time for that. I just make a stupid, a short comment. How do you relate your, assume that I have the ability to say something interesting, but how do you relate your research, this really amazing finding that people are so bad in remembering the distribution, how you relate it to the literature that says that people are natural frequentialists? Maybe if you would ask them what's a proportion of time you saw 84, they would be good. Have you tried something like that? Right, this is that's literature from the 80s that people are.
Yeah, well, it's really interesting that you say that, because we haven't. But that Hasher and Zach's work, the frequency counting stuff that always gets cited as people are really good at automatically encoding frequencies. If you go back and look at the experiments, they're incredibly simple. So they're things like, showing a triangle 4 times versus showing a square 7 times, or, they don't translate to people can represent a distribution or monitor frequencies in the way that those data often get cited as suggesting people can do. At least that's my interpretation of it. It may be that if we said to people, you know, did you see 84 more often than you saw 79, then they might be able to answer that kind of a targeted forced choice question. But the broader question that we're trying to get at is given, I mean, especially in some Bayesian frameworks, given the claims that are made for how people are representing distributions, can you actually see that people can acquire it in that way? And as I say, that the paper that we followed up on that by Tran, they used the kind of spatial distribution learning task. They had things pop up on the screen and people had to hit a key to make it disappear, using that same bimodal distribution. And they also found that people were completely horrible at it. They couldn't do it.
Yeah. This is very nice, because one of the justification for the common view of decision from experience that people just learn the distribution and then apply prospect theory, come up with the idea that people are good in remembering distribution. So in that respect, it converges with a mainstream decision from experience, different approach. That's very nice.
Thanks.
Okay, guys. So now it's time for those who have to leave us for other things to leave us. And thank you for coming. And those who want to stay can stay for about 10 or 15 more minutes. Ben, is it fine with you?
Yeah, I think I can stay awake for another 10 or 15 minutes. No, I'm fine.
It's already late for you. So after
it's 11 o'clock for me, yeah.
Oh, sorry.
And I've got to fly to the UK tomorrow, but that's fine. I'll be all right.
So it's a very good preparation.
It's true. I'm partially transitioning time zones already. That's right.
You see, it was a good timing. So if you have additional questions, this is the time.
Maybe I can continue with a deeper thought, not fully comprehend, that I'm just random thought. So you criticize two lines of research that are very different from each other, right? The people that believe in the barge kind of research say people are looking for complex pattern and without being aware of, and then they're going to respond to it. That they see that basically you say this guy is assuming too much. And on the other hand, you criticize two-stage prospect theory kind of literature. And basically most of application of prospect theory for decision from experience that assumes that people just remember distributions, prospect theory and similar. So, but it could be something in between. So, you know, one thing that worries me is that, so I think that your evidence against the idea that people remember distributions and is consistent with our research is also very convincing. But rejection the idea that some of the thing is people are not aware of, it's very hard to reject. Of course, it's possible to reject the idea that everybody the same unaware processes work for everybody, but maybe something are unaware, but each person in a different way, so you don't see robust patterns, but it's still there.
Yeah, I mean, I think I didn't go into the awareness stuff in as much detail because of the time, but I think one of the way I agree that they're kind of unrelated, and I'm trying to pull them together in the sense that the claims in both cases come from an insufficient testing of the representations that people are relying on in the different situations. And I think in the priming case, you know, we're quite comfortable with the idea that I respond to the word doctor faster if it's been preceded by nurse than if it's been preceded by some unrelated word. So that kind of ripple of activation, if you like, that flow of activation can go that far. But the claims that are then made that say, well, no, I can expose you to this word and 10 minutes later you're going to do something, you know, you're going to hit someone, or you're going to walk more slowly down this corridor, or you're going to rate this person as warmer or colder or whatever it might be, is stretching that river. So that was that that sort of boulder in a pond versus a pebble in a pond idea. That the pebble in a pond, the ripples go a little way, the boulder, they come right out of the pool. And there's the evidence, the tricky thing with that is that one, if you scrutinize the evidence on those kinds of priming experiments far enough, then a large number of them just don't stack up in the sense that they just don't replicate. They're just not real. Okay. So that you don't really need to explain them because they're not a real thing. And the ones that do maybe stack up can often be explained via alternative explanations that you haven't got to because you haven't actually tried to elicit the representation that people were using. And that's the whole notion of these correlated hypotheses, that I think as the experimenter, you're behaving in this way because it's consistent with my model of what I think the task is leading you to do. But in fact, there's another thing that's correlated with that, which is what's accounting for your behavior, but you fail to uncover it because you didn't ask me properly. You didn't actually elicit that that part of the representation of the problem. So that's, I think, where I'm trying to link it. And I agree that, you know, for different people, maybe there are different aspects that cause you to behave in different ways, some of which you're unaware of. But the stronger claim that the behavior in the kinds of tasks that we're interested in, the sort of higher level judgment and decision making, that people are being influenced by things entirely outside of their awareness or their representation of the problem, is just really difficult to argue for forcefully, I think, if you look at the evidence carefully.
Okay.
Oh, thank you so much, Ben. Thank you.
Okay, thanks, Kinneret. Good to see you.
Yes, Linda.
Hi, I just had a small question regarding the distribution creation or distribution builder experiment.
Yeah.
Regarding sort of expectations or prior beliefs, if you want to call it that, right? If I get a sequence, if I see a sequence of numbers, a bimodal distribution isn't sort of the most natural thing I'd assume is happening. And I thought sort of if it's a normal distribution, people are actually pretty good at representing that and in a distribution builder type thing, you know, squares actually recreating that. So have you thought of sort of manipulating the expectations, I don't know, via cover story or some other type to see whether your scaffolding or sort of assistance will work any better?
Yeah, it's good. It's a good question. I mean, there may well be more of a bias or a prior to think about things as normally distributed. We used the bimodal distribution to sort of follow on from the one that Tran had used, and they used it precisely for that reason, that they were interested to see, you know, can people acquire something just sort of via the experiential nature of it, not it being some assumption. But you can see from the data that you get from the sort of baseline experiment that people just reproduce something pretty flat, or they add another mode somewhere in the middle for whatever reason. On the distribution builder, yeah, that's a good point, that if you give people, you know, like the kind of Dan Goldstein style, literally a distribution builder, and say, slide these things so that you can, then people can, you know, you can elicit the underlying distribution and they can get it. But my claim would be that is already sort of giving people almost the entire representation first, because you're asking them to represent it in those sorts of terms. And so it's facilitating you building that up in a more structured way. So maybe you could get there, but it's not, it's different from saying that people can generate that kind of distribution themselves.
Oh, okay. I don't think I know the details of that, because we've used something like that, but we have had a different distribution. We just showed them a sequence of numbers, and then we give them that kind of tool to recreate the distribution. So they don't see an actual distribution first. Is that,
no, I understand that. Yeah, you see a sequence, but then you give them the tool to elicit the distribution. Yeah. And what I'm saying is that the tool in and of itself is partially solving the problem for them in a way that goes beyond, I guess, the level that we were interested in.
Cool. Thanks. Anyway, really interesting.
Thanks.
Thomas?
Hi, Ben. Thanks for the very interesting talk. So I have a thought. You know, one view of the mind is that we have a collection of a view of the mind that is more aligned with evolutionary psychology and also with the work by Iker Enser, is that people have specific rules for specific contexts. And so we have rules, for example, for deciding who to trust or who to form coalitions or cooperate with, and we have rules for navigating the environment, for searching, for foraging. And so my thought is, when we design experiments and we want to pin down the particular cognitive process, what we do is we strip context out completely. And what in a way, we're setting the conditions for people to construe the experiment to represent the problem in very different ways. Mm-hmm. So I was wondering whether those type of experiments that are context neutral, do you think are promoting this any representation goes, and complicating our own task of trying to see what people are actually doing? If we tell them, look, this is a foraging problem, people will deploy their foraging tools to operate, right? And so that's my thought. I don't know if you have thought about that.
No, I do. I absolutely do, because I think that it gets back to that issue of if you construct the mold sufficiently well, then you almost obviate the need to run the experiment, right? And so the flip side of having the completely context-free experiment is having the experiment where you say, here's the task, here's kind of what we want you to do, here's what we would, and then why would I, and then it's a question of, can people comprehend the instructions that I'm giving them, and the behavior kind of becomes secondary. So there's this difficult balance between constructing our problems so that they capture the underlying features of interest in the world that we're interested in, such as what are the factors that change the way people forage or choose between options, but leave enough out so that the behavior that we're still interested in is absent, and that we can measure it. And I think in the kind of classical economics side of things, they go to the point of saying, well, you don't need to run the experiment because we've described the world, and therefore this is the optimal thing to do, and therefore this must be the thing that people will do. And I sometimes wonder whether that's led in experimental economics to these situations where you have, you know, a 60-page set of instructions before you get to the experiment, so that people can be confident that, you know, they've understood exactly what it is that they have to do. So if they do something wrong now, it's not because they haven't got all the bits of the world. But yeah, I don't have an answer, but I have often had a similar thought, and I don't know quite how to solve it. But it's it's a really interesting comment.
I think it happens more in economics than in psychology, but sometimes in psychology as well.
Yeah.
Elliot, you have the right for the last question for today.
Well, very good. Thank you. So Ben, I have a question about a different part. So how far do you want to push this idea that there's no, I mean, in what context that there's no real unconscious biases influencing behavior? I mean, the example I'm thinking of, right, very different than what we usually do, but a gambling type experiment. It was the one from a few years ago from Paul Glincher's group with the, the people buying the lottery tickets after the Yankees win, right? Or if it's a sunny day after a streak of cloudy days. Obviously, I mean, it's not necessarily obvious, they didn't test this, but I would suggest that it is highly unlikely that people are taking into account the recent, performance of the sports team or the coincidental type of weather when making the real world decision of whether or not to buy a lottery ticket. But it seems to be robust. Now the question is, and that's like the sort of decision from experience, but actually in the real world. So do you think there's none of those types of influences, or we're just doing the experiments badly and we don't see them?
Yeah, I mean, I think that my my sense is that, well, yeah, the claims in general go way beyond the data, and that each, specific example or illustration needs to be carefully looked at, and really think about what the claim, what it is that people are supposedly unaware of in a given situation, and how that piece of knowledge is having a causal impact on what they're subsequently doing. Whether there can be a sort of proximal piece of information and they don't have access to the sort of distal cause of that information, but at the time of the choice, they're fully aware of why it is that they're doing what they're doing, and then that's driving it.
So you can think of something like mood as a mediator, and they'd be able to articulate, well, I'm in a good mood today, though they may not be able to say why they're in a good mood today, which might be related to a sporting event or weather change or something like that.
Potentially something like that, yeah. And then how far do you want to go back and say, well, you're in a good mood because your sports team won, or yeah. I mean, I think it's just that, again, going back to the generality of our explanations and going beyond common sense. It's very tempting for us to want to say as psychologists, oh, you think you know why you behave in this way, but actually you don't, because it's this magical unconscious influence that's operating. But yeah, I guess my answer is I want to push it quite far.
Okay. Well, I look forward to reading more when the book comes out.
Yeah, I hope you do. All
right.
Thank you.
Thank you, Ben, so much for coming, and hope
it's been a real pleasure. Thank you for the opportunity.
Flight tomorrow.
Good to see so many. I hope to see many of you in person again before too long. It's been far too long.
Thank you. It was a thought-provoking. It was very interesting. Thank you.
Great. All right.
Thanks, Ben.
Take care, everyone.
Good night.
Thanks.
Bye.
Bye-bye.
Bye.
Thank you.